Thanks, Zoltan, for a very nice introduction, generous introduction. I think you remembered all my topics. And thanks a lot for the organizers for organizing this wonderful workshop and having a nice program. And thanks for having me here. Okay, so today I'll be talking about some properties of Gromov-Wasserstein distance, and this will be in terms of some dual representations, what can we, some statistical questions, and also about the geometry of Gromov-Wasserstein. And this work is supported by my NSF Career Award, and this is done jointly with excellent collaborators. The heavy lifting is done by Zhengxing Zhang, who is currently a PhD student at Cornell, and Zhu is an assistant professor at Cornell, and Christian and Yusuf, they are researchers at IBM, New York. Okay, so before I actually get on to Gromov-Wasserstein distance, since the distance is, as we already have heard to Remy in the morning, so since this is based on this notion of optimal transports, I'm just going to give you a very quick primer on optimal transport. Just also, it will help me to kind of capture the notation and everything as we move on. So as we know, optimal transport, it started with this question raised by Munch in 1780s. And from then, there has been like a rich set of mathematicians working on this topic and have contributed to different areas of mathematics. Particularly, the optimal transport became popular because of its connections in different areas such as like probability, geometry, PDEs, and physics, and so very classical areas in which a lot of contributions have been made. But optimal transport also made its way into machine learning and statistics. There has been a lot of interest in machine learning and statistics over the last decade. So you see there is this new area of statistical optimal transport, and people are using optimal transport to solve statistical problems, very classical statistical problems like sampling, variation inference, so on and so forth. And this has gained a lot of popularity over the last decade. Okay, so just to start with this problem of optimal transport, Munch asked this question saying, suppose if we give two probability distributions, mu and nu, okay, and then there is a certain cost function C that is given. We want to find a transport map. So we want to find a transport map that basically solves this problem. Okay, so the transport map is basically satisfying this thing, which is, it is a push forward of the measure mu, giving the measure nu. So here in this picture, we can think of this measure mu to be like, I want to basically excavate some amount of sand. That is, I want to excavate like a measure mu of sand, and I want to transport it, and I want to build a factory, right? And that factory basically has this measure nu. We just basically, there is no loss of mass in the transportation, so on and so forth. Essentially, the whole excavated sand is used to construct this factory. So of course, there is a cost involved in basically doing this transportation, right? So we want to basically find this map T that kind of makes this overall cost of transporting from mu to nu in the most effective way, right? So this is the problem that Munch formulated. And then one can ask, since this is an optimization problem, one can ask the question saying, okay, first of all, does the solution exist, and is the solution unique, so on and so forth. And as you can see here, the solution need not exist, right? So because if your measure mu, if this is a Dirac mass just supported on one point x, and nu is a measures with two Dirac masses supported on y1, y2, and because the way this problem has been formulated, T has to be basically a one-to-one map, and in this case, the measure transportation, the solution does not exist for the Munch problem, right? So then came Kontrovich. Kontrovich basically posed a relaxed version of the same problem, right? So rather than having this map to be one-to-one, by which basically transports from mu to nu, Contra-Wedge actually posed the problem in a different way, where the question is, you want to find a coupling. The coupling is defined as a joint distribution on the space of, it's basically a joint distribution such that the marginals are mu and nu. Okay, and this is called as either a transport plan or coupling. And you want to basically find this transport plan such that this cost is minimized. Okay, so what is the advantage in this formulation? The advantage in this formulation is essentially, unlike in this case where x can only go to only one point, in the Cantor-Wedge formulation, x can basically go to multiple points, or multiple x's can basically go to the same y, right? So, and as you can see, we are doing this optimization over pi, and the objective is linear in pi. So this is a linear program, and the constraint set is a convex set. So this is a linear, therefore this is a linear objective with a linear constraint. So therefore this is a linear programming problem. And the nice thing is, this also recovers the Munch formulation, which means, suppose if there is an optimal Munch map, which I denote this as T star, then the optimal transport plan or the coupling can be obtained by doing this operation. Okay. So this is all very classic, well known. And then one of the key things that actually allows us to understand the structure of the Wasserstein distance is the duality, right? And the duality will play a key role for the rest of the talk once we actually move on to Gromov-Wasserstein. So in this case, I'm considering the cost function to be the two distance, the L2 distance between the points x and y. Okay, and this is defined as the Wasserstein distance, and we have a dual representation for this distance in terms of the Contra-Wedge potentials. So this phi and psi are the Contra-Wedge potentials, and based on these potentials, there is this very famous, or in fact the cornerstone theorem of optimal transport, which is Brenner's theorem, which basically says if the measure that you're trying to transport, which is mu, if it has a density with respect to the Lebesgue measure, then the Munch formulation and the Contra-Wedge formulation, they basically coincide, and the Munch map is actually given by the gradient of phi star, where phi is basically the Contra-Wedge potential that appears in the dual form. Okay. Okay. So now, I mean, we already saw like many applications of Wasserstein space so far. Yesterday we had this nice talk by Victor. So as you can see that if you are working with Dirac measures, then the Wasserstein distance between the Dirac measures is simply the Euclidean distance between the points. But then it has like a lot more richer structure, right? So one can actually talk about barycenter, geodesic flows, geodesic curves, and then it has, one can define gradient flows, which I'm going to get back in the second part of the talk. And some of these things have been used to actually solve these problems in classical problems in statistics, which include like sampling and variation inference and so on and so forth. Okay, so having some background on optimal transport and Wasserstein distance, now we want to basically go beyond these concepts. And the motivation is the question of dealing with heterogeneous data, right? So suppose I have two distributions, right? Let's say they're defined on inhomogeneous spaces, right? So maybe I have a distribution on RD1 and a distribution on RD2. How do you basically measure the similarity or dissimilarity between these distributions? So if I'm using Wasserstein distance, the distributions are defined on the same space. Okay. Now if the distributions are defined on different spaces, how do we measure the similarity or dissimilarity between them? So that's the question. So various applications of this question basically requires like kind of matching heterogeneous data sets. So here is the problem where I'm given, I want to, let's say, build a dictionary from English to French, right? So you have a collection of words which are mentioned, which are shown here as blue dots, and then you have the collection of French words which are shown as the red dots. Which means we have two different distributions on these languages, and we basically want to kind of, now if I want to build a dictionary, you want to in some sense do a comparison between, for example, the man should get mapped to Home, so on and so forth, right? So how do we do this? Right. The another question that one can ask is structure preserving interpolation, right? So let's say we have this is the source horse and this is the target horse, right? So I want to basically interpolate from the source to the target, and we can do this using the Wasserstein geometry. Okay, so using this Wasserstein distance, one can actually interpolate from the source to the target, and when we do that, we basically get the intermediate pictures to be like this. And the only problem is these horses seem to have some mustache, right? So which means there are some extraneous objects which do not really kind of maintain the structure. Ideally, what we would want is to preserve the structure, right? So with these two aspects in mind, we consider the Gromov-Wasserstein distance. So this is our motivation to consider this distance, and it's not like, I mean, this distance has been actually pretty popular in the community. It's just that we are motivated to kind of understand more on the foundations of some questions related to Gromov-Wasserstein, given that a lot of things were understood about Wasserstein. Okay, so what is the setting? So here the setting is we are going to treat the data sets as metric measure spaces. So which means I have two spaces x and y, and each of them are endowed with metrics dx and dy, and they also have a measure defined on each of them, mu and nu, right? So now if I want to compare between distributions that are defined on these two incomparable spaces, we want to basically define a map T, which is basically a transport map, so that the push forward of mu gives me nu. But at the same time, we want to kind of preserve the local structure in each of the spaces, right? So which means, so we look at the distance between the points in the input space, the x space, and we also look at the point, after we do the transformation through this map T, we look at the distance between points in the y space, and these things, they shouldn't be too far. So with this motivation, the Gromov-Wasserstein distance was proposed by Memoli, right? So the Gromov-Wasserstein, I'm just using the notation 2, 2. So 1, 2 corresponds to the 2 here, and the other 2 corresponds to the 2 here. Okay. So the Gromov-Wasserstein is now defined in the optimal transport flavor. It's just that now my cost function is precisely this. Okay, so it's no more linear in pi, it's basically quadratic in pi, as you would have seen in the first talk, right? And this Gromov-Wasserstein distance is 0 if and only if there exists an isometry T, right? So if this is 0, which means we want that this cost basically is 0. So which means we basically have an isometry such that T also is a transport map. Okay, so which means that basically defines a set of equivalence classes, and the Gromov-Wasserstein is a metric on the equivalence classes of metric measure spaces. Feel free to stop me if you have any questions in between. Okay, so with this introduction, so this will be our roadmap for the rest of the talk. So I introduced the Wasserstein distance. So again, when I say the Wasserstein distance, I'm just going to look at the W2, and the Gromov-Wasserstein I'm going to look at is GW22. Okay, so this is what we'll work with. Okay, so I already introduced you the dual representation of the Wasserstein. Okay, so we will see how the dual representation of Wasserstein has played a role in addressing some statistical questions. Okay, and then that basically motivated us to kind of consider, can we get a dual representation for Gromov-Wasserstein? And the idea is, can we ask the same questions, statistical questions for Gromov-Wasserstein? And it turns out that the dual representation is the key. And therefore, this will be like the first part of it. And then once, the second question we see is, the duality also plays a key role in understanding the gradient flows that are defined, the Wasserstein gradient flows. Okay. So now, having obtained a dual representation for the Gromov-Wasserstein, we ask the same question: can we actually build Gromov-Wasserstein gradient flows? Okay, and then we will see this Gromov-Wasserstein gradient flows allows you to do the structure preserving interpolation. Okay, and then there is also like an interesting Riemannian structure that comes out of this whole analysis, and the interesting bit is it has very close connections to optimal transport. Okay, because of the way GW is posed. I mean, it's not classical optimal transport, but it has a quadratic form in terms of pi. But because of its kind of the feel of OT that is sitting in there, you will see there is optimal transport, like it appears very naturally in all these questions that we are trying to address. Okay, so the first question is the question of estimating the Wasserstein distance. Suppose, let's say I give you samples, IID samples from mu and IID samples from nu. The goal is, what is the rate of estimating the Wasserstein distance? Okay, so one may ask, why is this question important? Of course, this question is important because we already have seen this problem of testing whether these two samples are coming from the same distribution or not. I mean, right? So the two sample problem. So to solve a two sample problem, yesterday we saw about this Procrustes technique, or I can also use MMD or variants of it. So why not use Wasserstein, right? So if you need to address a two sample problem using Wasserstein, so we need to have a test statistic, and the test statistic will be based on estimating this distance involving the samples. Okay. Okay, so this is a very classical thing. It was, I mean, in fact, addressed in 69. I think some references are missing here. There is also work by Fournier. So the point is the estimation error rate of the Wasserstein distance square is n to the negative 2 over d, right? So of course, people who are fans of MMD, one can argue that, okay, I mean, MMD doesn't have any dimension dependence in the rate, it's dimension dependent, right? But of course, Wasserstein suffers from the curse of dimensionality. And the key idea in proving this result is basically the duality. Okay, so we already saw this dual representation. Right? This is written in terms of the contra-Mitch potentials phi and c. And once we have the dual representation, now you can see if I want to estimate the Wasserstein distance based on the samples, all I have to do is replace the measures with the empirical measure. Okay, and then do the routine calculations, and then by triangular inequality you can basically write this as the expected suprema of an empirical process indexed by certain function classes f and g. Okay, so of course here, if you do like a nice control, you can get like reasonable classes. F and G will be reasonable classes, and then there are standard results in terms of the covering number, the chaining arguments, which basically gives you this rate of n to the negative 2 over d. Okay, so the duality plays a key role in obtaining these rates. Right. So there is also a variant of this Wasserstein distance called this entropic optimal transport. Right. The reason the entropic optimal transport, we have a master here. He is so the entropic optimal transport was introduced basically to make the computations of the Wasserstein distance faster, right? Because the Wasserstein distance, the cost function is not strictly convex, so therefore you basically kind of make the cost function strictly convex by introducing the entropy term. And then as you see that as epsilon becomes larger and larger, you are basically making your transport plan to be to have a larger entropy, so which means it basically becomes more diffusive, and this basically allows your cost function to be strictly convex, and there are these effective algorithms which basically allow you to address this question very well, right? So I mean, I'm not talking about any algorithms here. But since this is something that has been used in practice, so one can also ask the question of, if I want to estimate this entropic cost, right, based on samples, what is the rate of estimation? The rate of estimation, interestingly, does not depend on the dimension, right? So of course, you have to pay for the approximation error there, because if you want to exactly estimate the Wasserstein distance, then you need to look at the distance between your entropic cost to the actual Wasserstein distance, and that basically is dimension dependent, so you cannot basically beat the curse of dimensionality. But nonetheless, this is something that people use in practice, and the rate of convergence is like MMD, like no dimension dependence. Okay, so now we want to ask the same question with respect to the Gromov-Wasserstein, right? Suppose if I want to estimate the Gromov-Wasserstein based on samples, so how do I do that? So before I ask that question, we first get this duality result, right? So the duality result here is, again, when I introduced Gromov-Wasserstein, let me go back. When I introduce Gromov-Wasserstein, this is pretty generic. So there is a certain metric. There is a certain metric on the X space. There is a certain metric on the Y space. So this duality result that I'm going to present, I'm going to work with the Euclidean distance, right? The spaces are different. So there is a dimension RdX. The space X is RdX and space Y is Rdy. Okay. So the dimensions of the spaces are different, but the metric, okay, is a little bit of overloading of notation. So if you're careful, not quite overloading, because this is d subscript x, which is the metric on x, and the metric on x and y, I use the Euclidean metric, okay, but the spaces are still different. And we want these, the measures mu and nu, they need to have the fourth moments, okay. Under this case, we can write the GW22 square in terms of this crazy formula, okay. I mean, it looks crazy. You can ignore all the terms that involve the black ones, okay. So what is more important is the red one, and the reason you can already see why I am working with the 2 and the Euclidean distance is because I am looking at like some distance square minus distance square and then whole square. So this is something easy to compute, so you can do a lot of calculations by closed form, and that is how you can see like there are these 4 powers that appear, okay. So the way I am showing the result here is I collect all the terms which involve the transport plan pi, right? So the red terms involve pi, and the black terms does not involve pi. It only depends only on the marginal measures, okay. Okay, so let's get to the red term. So the red term is basically telling, if you look at this object is precisely an optimal transport problem, okay, with a specific cost, and that specific cost is this, right? So the inner problem, so you basically write your GW problem as basically 2 minimizations problems, one over the transport plan and another over some matrix A that is appearing, okay. And the inner problem is basically a collection of OT problems indexed by this matrix A, okay. So which means, because this is an OT problem, I can write the dual problem for the OT problem, which is precisely the bottom one, okay. So this dual representation is useful in addressing this question of statistical estimation, because as you can see, if I give you samples from distributions, you can replace mu with mu hat and nu with nu hat there, okay. So this term can be estimated, and the remaining terms will simply depend only on mu or nu, so they can be estimated at a rate 1 over root n, okay. So all that matters is basically the analysis of the red term. Okay. Right. So here is the result. So if we have, if you are given two sets of samples, and if you want to estimate the Gromov-Wasserstein between mu and nu, the result says, okay, so this result, of course, there is a curse of dimensionality. The key point to note here is the rate here depends on the minimum of the dimensions between the input space and the output space. Okay, so that's the key one. And then this 1 over root n quantity is appearing from these terms. Okay, so it's only the estimation of this object is, of course, has a dimension dependence which behaves like this. And in fact, this bound is tight. So you can basically show that up to constants, this bound, there is a lower bound. Okay. And the idea of for the upper bound and lower bound are as follows. For the upper bound, again, if you just by staring at this term, so essentially we take the population version and then we take the empirical version, and then we can essentially see that all we have to do is bound the population version of this, or rather the dual form, to the empirical version. So that is one term that appears, and the other one that appears is the rest of the black terms, which basically can get estimated at 1 over root n, right? So the clear thing is we are looking at the estimation of a collection of optimal transport problems indexed by this matrix A. So again, you have like a suprema of this will end up in a suprema of an empirical process, and use like similar tools as in Wasserstein distance to get those rates. Yeah.
But A can have an arbitrarily large volume, no?
Yeah. So I have. So I haven't. So yeah, you can show that all the entries in that matrix A, they're all bounded, and that is where these conditions about, for example, so here I said mu and nu have like the fourth moments, and the entries in A, you can show that they're all bounded by those moments. Yeah, I didn't want to, I mean, already the slides are a little messy. I didn't want to make it so rigorous that it is more messy. So yeah, right. Okay, so that is for the upper bound, and for the lower bound, the idea is, so this is an interesting side lemma. So this lemma basically kind of relates the GW to W2, and it basically says GW is lower bounded by a Wasserstein procrustes, right? So all we are doing here is we are looking at the distance, Wasserstein distance between mu and a transported version of nu, where the transported version is basically like transported through an orthogonal matrix, right? So which is precisely like a procrustes method with Wasserstein as the distance. So you can control GW in terms of Wasserstein, and then all we need to show is we basically have to construct like two measures mu and nu, and we choose these measures mu and nu to be these uniform measures on this ball of radius 1 and ball of radius 2, and doing some calculations we can basically show that you can actually reduce this problem of estimating the distance between two sets of samples. You can reduce this problem of reducing the distance between one set of sample and its population measure. Okay, so that is this question, which is further lower bounded by this one, and then using the classical result. So this result is very well known in the literature, right? So because the rate that I showed of n to the negative 2 over d, that is for W2 square. Okay, so W2 is like n to the negative 1 over d. So from there, so you know that those rates are optimal. So using this result, so therefore we basically establish the lower bound. Okay, so again, similar conclusions can be derived for the entropic GW. So we can look at the entropic version of the GW, where this is the GW22 using the Euclidean distance, and then here we have the entropic part. And again, as in the case of, because end of the day analysis is very similar, right? So once you have the dual form, the analysis basically goes through the analysis of the optimal transport estimation. So again, up to constants, we get a rate which is like 1 over root n. Yep.
Regarding the dimension dependence, here it seems to depend on the work dimension, right? The x and the y.
So here it is the maximum of x and y. That's what it is. Yeah, so I think we were probably not super careful here. Okay, we are probably focusing more on the 1 over root n part than on the constants. But in the other case, in fact, the other case was actually interesting. When we submitted the paper to Annals, we actually had the result with the maximum in the rate, so which is actually not good, right? And then one of the reviewers actually pointed to a paper which actually helped us to fix that one, so we could have the minimum. Yes?
Related to this, if the intrinsic dimension is lower, the spirit of the work of Ole and Luke,
Exactly, it's exactly that paper. It's exactly that paper. Yeah, it is that paper. Yeah, yeah, LCA, yeah. Oh, you heard the referee? Yeah, precisely we use the principle, yeah. Yeah, it's a very elegant idea, yeah. Any other questions? Okay. Good. So that is the statistics question. So now we'll move into the gradient flow question. Okay, so now we'll move into this gradient flow question. So before I move into the gradient flow question, I will again start with like some basics just to ensure notation, everything is set up. So I'll start with the gradient descent, which all of us are familiar. I'm pretty sure all of you are also pretty familiar with gradient flows, but just to, I don't want to assume anything, so therefore I'll start with the gradient descent. So let's say I have this function f and I'm trying to minimize this over Rd, right? And let's say f is differentiable. So gradient descent update is like this, right? So you basically move in the direction that is in the negative of the gradient of the function, right? And why is this a reasonable thing to do? This is a reasonable thing to do just by doing a Taylor expansion of this f at xk plus 1, right? So you can basically see that choosing this type of an update, it basically ensures your function is decreasing at every step, right? So therefore gradient descent is it's a reasonable thing to do. And what is the gradient flow? Gradient flow is basically a continuous version of this gradient descent, right? So where there is no step size. So the gradient flow is defined through this ODE, where it says if I think of x of t as the position of a particle at time t, then x dot is basically the velocity of that particle, and I'm basically saying the velocity of the particle is basically defined by this gradient. Okay, so this is, and here we call this as the Euclidean gradient flow because the gradient of f is defined in the usual sense in Rd, right? And what is the nice property with this gradient flow, because now if I look at what is the rate of change of my function, by simple chain rule, you can basically see that this function is decreasing, right? Along the flow, this function f decreases. Okay. So, which means I have this ODE. So we can actually discretize this ODE, right? So one way to discretize this is called the explicit Euler, and explicit Euler is precisely your gradient descent, right? So if you see, I have xk plus 1 minus xk divided by the step size, and if I make the step size to basically go to 0, you can see like it is in some sense the left hand side is kind of approximating the gradient of the function, right? Is basically approximating to x dot, and the right hand side is looking like the negative gradient of f. Okay. Okay, so this is called the explicit Euler scheme, and the implicit Euler scheme is the proximal method where this looks like the gradient descent, but it's just that this is computed at the next update. Okay, so this is the difference between these two updates. So in fact, this update can be written in this fashion as an optimization problem. And so essentially this is telling, okay, I want to minimize the function, but at the same time I don't want to be too far away from the past iterate, right? And that's where this name proximal method comes. So it is well understood that implicit Euler is a more stable discretization than the explicit Euler. Okay, so some fundamentals on this, right? And then one more thing that I'll introduce is the continuity equation. Okay, so there are two different ways of looking at the same thing. So let's say the first one is the ODE that we already saw. This is basically saying, okay, what is the velocity of my particle at a certain time, where the particle is driven by a certain vector field V. Okay. The other way to think of the same thing is you basically at a certain point in time, you basically look at what is the rate of change of mass of particles going through at a certain time. Okay, and that is basically captured by the continuity equation. The continuity equation, it simply says if I have these particles driven by a vector field Vt, the rate of change of mass at a certain point is basically the amount of mass that is coming in and going out, right? So the mass is conserved, which is basically the continuity equation. Okay, and this continuity equation can also be thought of as, so let's say you have this push forward of, you start with the measure rho 0 and you do this push forward by xt, where xt is defined above, right? And then if you look at, and then you can show that this rho t actually satisfies this continuity equation. Okay, so now what is this gradient flow? The gradient flows, you say a certain evolutionary equation. So in this case, this is the evolutionary equation. So this equation has a gradient flow structure if this vector field Vt is the gradient of some function with respect to some geometry. So there has to be some energy function that I'm trying to minimize. Okay, so in the case of Euclidean gradient flow, the geometry is Euclidean, but it doesn't have to be Euclidean, right? As long as I can establish that there is a function and there is a geometry which can yield the vector field, then you basically call this as, this has a gradient flow structure. This PDE has a gradient flow structure. So Wasserstein gradient flow has been pretty popular, right? So what do we mean by a Wasserstein gradient flow? So let's look at the classical Euclidean gradient flow. So here I have a function defined on Rd. So this is the Euclidean gradient flow which I already introduced, and we saw that this Euclidean gradient flow, I can discretize this in an implicit Euler way, which basically gives me this proximal algorithm, right? And of course, if I make the step size tau to go to 0, you can basically recover the, so as tau goes to 0, so we can recover back this ODE. Okay, so this is in the Euclidean setting. Now let's consider a functional f that is defined on the probability space. Okay, so now I want to define this type of a flow on the probability space. So which means I have a curve. As I'm evolving over time, this curve is basically taking different values in the probability space. Okay, so you basically now, I mean, this is precisely, in this case, xt was the position of the particle. So here we can basically say this is the, as I'm moving in time, the curve is basically taking values in the probability space, and we want to basically see how do you define a gradient flow, like we defined in the case of Euclidean case. How do you define a gradient flow in the probability space? Okay. So in other words, how do you define these updates in the probability space? Okay. So there is this almost, it's a foundational work by Jordan, Kindle, Lehrer, and Otto. right? It's called the Jacobi scheme. Sometimes it's also called as the minimum moment scheme. What they proposed is, let us define this update in this way. If you see, this update is pretty much similar to your proximal method. It's just that instead of this Euclidean distance, I replace this with the W2 distance. Right? So the geometry is defined, the cost is defined, or your functional is defined, f is defined, and your geometry is defined. And you use this as a way to define how you want to move in the probability space. Okay. And now they did the same analysis, which is they allowed this tau to go to 0. Okay, so you keep reducing this penalty term, and they showed that you actually recover the continuity equation where the vector field is defined in this fashion. Okay, so this is the gradient of, so the delta there is the first variation, so just think of this as like your that's your directional derivative or the Gauss derivative. So this is the negative gradient of the first variation of your function. Okay, so this they established, and so which means, so now we can write your dou t mu t. If I want, I can write this as the negative gradient sum W2 f of mu t, right? So if I write an equation like this is precisely my gradient flow. I still don't know what do I mean by gradient W2 of f, but that is basically my gradient of my functional in W2, but that is my gradient flow equation. Okay, so you can clearly see from this continuity equation expression, from this expression, because Vt takes this form, you can clearly see that the gradient of your functional with respect to the Wasserstein is precisely the negative divergence of mu times the gradient of the first variation. Okay. So why is this important? Actually, this whole work became super famous. It's mainly because suppose I choose my functional to be entropy. I mean, here it is the negative entropy here. Okay. So you want to maximize the entropy or minimize the negative entropy. So we choose the negative entropy. So if I choose the functional to be this negative entropy, what happens to the gradient flow equation? The gradient flow equation reduces to the heat equation. Okay, so people have understood heat equation from the probabilistic perspective, diffusion processes, right? It's very well understood. And what these guys gave is a variational perspective for this PDE, right? And that's how the optimal transport and PDEs they merged very nicely, right? And of course, if I choose the functional to be the KL divergence, you exactly get the Fokker-Planck equation. Again, this is like extremely classical one, right? Which is like the driving force behind all this Langevin-based sampling algorithm, so on and so forth, right? So there are these nice connections between optimal transport and PDEs. And what more? Because and they also basically recovered a nice Riemannian structure, right? So the tangent space is basically identified with L2. So as we saw in one of the talks, essentially it is like the gradient of convex functions, infinitely differentiable convex functions, and you take a closure with respect to L2, right? And the Bellamy-Brenier formula, it is the one which gives the Riemannian structure to the whole space, right? So basically, this is precisely the way you define a Riemannian distance, where this acts as your Riemannian metric tensor. Okay, so this is precisely how you would. So this is the result which Bellamy-Brenier showed, from which you can basically argue that okay, there is this nice Riemannian structure on, and this is a pseudo-Riemannian manifold. So you have a Riemannian structure. The metric tensor is well defined. So all these things are like supremely understood for the Wasserstein. So now we want to kind of understand something similar for GW. Okay. But suddenly now I have changed. If you see, my title suddenly has changed. There is some change. What is the change? Like I introduced a new thing called the inner product GW. Okay. So my GW, previously I was looking at the Euclidean distance square minus, right? So this is what I've been considering so far for the statistical problem. So when we wanted to study the flows, of course, we wanted to actually study this subject only, the one that I've shown in red. But it turns out that it doesn't have a Munge map. Okay, so it is basically the Munge map allows you to kind of do all these nice things in the case of Wasserstein. So it doesn't have a Munge map. So we basically decided to change the way you measure the similarity between the points. Previously we used the distance, now we use the inner product. Okay, and this basically, and I'll show this result, this basically shows that there exists a Munge map, and that is precisely driven by the Brenier map that is coming from the optimal transport. Okay, again, since I have changed the cast, I'll again prove a new duality result. Again, nothing fancy, it's very similar to what we had before, right? Again, this has collection of terms. This depends only on the marginals mu and nu, and here is a collection of OT problems. So I'm optimizing over a collection of OT problems. The cast is slightly different to what we had before, and here is the result that we could show, saying that suppose if pi star is the optimal IGW coupling, so we call this IGW for the inner product GW. If pi star is the optimal IGW coupling such that this matrix A star, which I have defined, is non-singular, then this basically shows we can recover this pi star through this Munge map T star, where if you see this T star is defined through this one, which is precisely the Brenier map that is coming from solving a classical OT problem. Okay, so if I solve this OT problem with A star, so if this is my OT problem, if I choose my cast CA, where A is replaced by this optimal A star, then that Brenier map gives me the Munge map for this problem. Okay, so then the recipe is similar. We do the same JKO, but now replacing W2 with IGW. Okay, so now we can ask the same question: what happens in the infinitesimal limit? As tau goes to 0, what sort of evolutionary equation does this converge to? So we can show that again you have a similar type of the continuity equation, but just that now the vector field that you have is basically, so this is the Wasserstein gradient, and the vector field now is basically a linear operator acting on the Wasserstein gradient. Okay, and how is this? It is inverse of this operator L, and this operator is defined in this fashion. Okay, and we call this operator as a mobility operator. So the interesting thing is this operator has two terms, right? So this is a local term. So I pass the vector field V to this operator. So this term just looks at the vector field at a point x. Okay, so this is the local thing, whereas the second term, it basically looks at this vector field everywhere. So that is the global term. So you need the global term because I want to basically preserve the structure. IGW tries to preserve the structure. The W2 does not look at the structure. It basically wants to kind of minimize the functional as best as it could, right? Whereas the IGW, we want to preserve the structure. Because you want to preserve the structure, you need to know something more about the global information. So this operator takes into account both the local information and the global information. So therefore, the corresponding gradient that we consider that has both the local and the global information. Okay, so if you basically drive your particles along this vector field, you basically get the fastest decrease in the functional, right, with the least distortion in the intrinsic structure, because we want to basically preserve the local structure, but at the same time want to minimize the functional. Yeah.
Is there inversion?
There is a notion. I'll talk about it.
Is it always invertible?
I'll talk about it now. So that's the second thing should answer your question. It's not invertible, right? So the null space of this operator is basically the skew symmetric linear transformations. So when I talk about the inverse, so I'm basically looking at the inverse on an invariant subspace of this operator. Okay. So what do these operator L and L inverse do? So basically these operators, they serve to kind of align the movement such that you preserve the global structure. So as you see, so here I start with, this is my original, right, and this is like L applied twice, L applied thrice, 4 and 5 times. Similarly, this is L inverse applied twice, so on and so forth, right? So as you can see, these vector fields basically they kind of line up, okay. There is another interesting phenomenon that happens in this IGW geometry is there is notions of both descent and damping. So in the case of Wasserstein, there is only descent. So I just basically want to minimize my functional as best as I can, okay. But here, if I look at what is the rate of change of my functional, in the case of Wasserstein, you will not have this and you will not have this. The rate of change of this functional is simply the norm square of your Wasserstein gradient, okay, and there is a negative sign there, so you know that your functional is always decreasing when you are moving along that flow, okay. With respect to the IGW, there are two terms. So first of all, this term is reducing. The sigma is essentially the covariance matrix defined at mu t with respect to mu t, okay. So the first term is a negative term, so there is a decay in the functional. The second term, I did not write what the second term is. The second term is a messy one, right? So I didn't want to, I just want to give you an intuition that the second term is actually positive, okay. So if the second term is also negative, you know that of course your function is always reducing, right? But the second term is positive. The first term is your descent term, which is aligned with your Wasserstein flow structure, because I am looking at, in some sense, a deregularized Wasserstein gradient there, okay, because it is the inverse of your covariance matrix. The second term is the damping term. It is positive in the sense it basically slows down the flow because it wants to preserve the local structure, right? It doesn't want to move too fast because it wants to preserve the local structure, but the first term basically drives the energy function to decrease. So here is a picture, right? So the functional that I am working with to minimize here is negative entropy, okay. So look at this Wasserstein flow. So which means if I want to basically minimize entropy, which means I'm maximizing the entropy. So I start with a distribution which has a very small entropy, and as I move along the flow in the Wasserstein distance, this is what I obtain after time 5, after 5 iterations. So which means my particles have become more random, so the entropy has increased, okay. And this is what happens with IGW, okay. So as you can see, the particles have moved, but they are not as random as compared to the Wasserstein, okay. Here are the two terms that I mentioned. One is the descent term and other is the damping term. So the damping term does not allow you to basically descend as fast as you could if you were actually working in Wasserstein geometry, okay, and that allows you to preserve the local structure. And this is, we also ran the simulation just to check, and this is the case where the entropy reduces quite a bit with the Wasserstein, whereas it doesn't decrease so much in the case of IGW. Okay, in the interest of time, I'll skip that. Okay. So the tangent space in the case of this IGW is again the collection of, it's not the entire L2 like in the case of the W2. Right, so this is basically, it's a collection of all those vectors such that this object is symmetric, and then you can define a Riemannian metric tensor, and the metric tensor is defined like this, right? So again, the metric tensor here, it takes into account both the local information and the global information through this mobility operator. Okay, so this is a slightly more technical result. I don't want to, I can talk if someone is interested later. So this is a version of Gromov-Wasserstein with respect to IGW. Okay, so maybe I'll say this and leave it there. And okay, so the thing is, Riemann structure is all you need. So if we start with this continuity equation, right? And from the continuity equation, if I am looking at what is the rate of change of my functional, this is a straightforward thing to derive. Okay. So this one we can we can write it in two ways. So clearly this one is precisely the L2 inner product of this gradient of the first variation with respect to your vector field Vt. That is one way to do it. Or the other way is I can use this metric tensor that I have defined on the IGW space, on the tangent space of IGW, okay, and I use this L inverse operator. Okay, so it's a simple calculation because the metric tensor G mu is defined with respect to L, and I'm basically cancelling that by introducing L inverse. So you basically again get back your usual L2 inner product. Okay, so from this we can basically recognize that this corresponds to the Wasserstein gradient and this corresponds to the IGW gradient. And once we have this gradient, then we can actually write a Gromov-Wasserstein on the Wasserstein space. This is Gromov-Wasserstein on Wasserstein, and this is Gromov-Wasserstein on IGW. Okay, so just as a teaser, so here again we started with this motivation of doing interpolation by preserving the structure, right? So here is this cat example. So this is my source and this is my target. I basically want to rotate my cat to 90 degrees, right? So as you can see, I don't know how well you can see, I can't see that well from here. This is the IGW flow where this cat structure is very well preserved. Both of them basically go to the target, right? But along the way, the structure is not preserved in the case of the Wasserstein flow. Okay. And here is another example where I basically want to now transport my cat into a heart, right? A rotated heart. Okay. So, of course, here you need to take into this information, this local information, and so this is the type of interpolation that one can achieve. Okay, so to summarize, we looked at some theoretical properties of this GW distances, particularly motivated through duality, and we could answer some statistical estimation questions and also some geometric questions related to gradient flows and Riemann structure on the IGW space. With this, I thank you, and I can take any questions you may have.
Thank you for the nice talk. So it's time for questions.
Is there anything on the curvature of IGW?
We don't know anything of that. Yeah.
Because you have these two components in your flow, something local and something global. When you do discretizations, have you run some ideas how these two things play along? Can you choose something I don't know, finer in the other one and bigger in the other one according to some criteria or?
That's a good question. I think we haven't really thought much on the implementation issues. As you see, like these are simple toy examples we played with, but I think that's a good question. Like maybe you do fine discretization on the global part, and like probably then that is kind of going to preserve a lot more local information. But then maybe your flow may be also going slow. So there could be a trade-off between like the dampening versus the descent. Yeah.
Thank you for a great talk. This is going to be a bit of a vague question, and I'm sorry. Do you know if there are generalizations if what you're looking to preserve is not a metric but a semi-metric or some criterion like faithfulness to a set of labels?
I don't know.
Okay, thank you very much for enlightening talk. I was curious, maybe it's a naive question about when you approximate the Gromov-Wasserstein, no, the Gromov-Wasserstein or Hausdorff distance by the empirical. Is there any study on the second order, that is the central limit theorem? That is, it's available
I think there is a recent work by my collaborator, like Ziv from Cornell. I think he has a follow-up work on a central limit theorem for the estimator.
Okay.
I mean, I may be wrong, but as far as I know, I think he has a result. If not, there is a problem to work on.
One question which I was wondering, so this, when you introduce this product, Gromov-Wasserstein distance, you use the classical Euclidean product, and afterwards, when you use it in this gradient flow, the covariance matrix showed up. So could we kernelize it? Maybe possibly with covariance operators?
No, actually, we are currently working on it. So in the sense, you replace the inner product cost with the kernel cost.
Kernel on the X space, kernel on the Y space.
Kernel on the Y space.
And
then you can go to some extent on this gradient flow question, but I don't think we have completely understood on the geometry side of things. I think most of these things like that we have in this manuscript will carry forward even with the kernels. But the question is, are there any interesting kernels, right, that basically reveal you something more than like what you see with this inner product thing? So we don't know that.
Okay, so is another question. Let's thank the speaker again.
Thank you.